Okay, so we'll continue with power series solutions for linear equations. If you remember from the last two lectures, we focused on the second order homogeneous linear equation. Homogeneous is when the right-hand side is equal to 0. It's a linear second order equation where you have coefficient functions ax in front of the y double prime, and then bx in front of the y prime, and a cx in front of the y. We had the notion of an ordinary point. You say that x equal to a is an ordinary point. If you can normalize this equation, normalizing the equation means that you divide the two sides by ax, so that the equation becomes something like this: y double prime plus pxy prime qxy equal to 0. You say a is an ordinary point if after you normalize the equation, the coefficient functions px, qx both have convergent Taylor series near the point x equal to a. Now, we only look at the special case where a is equal to 0, so the origin is an ordinary point. And in this case, it is guaranteed, we had a theorem, it is guaranteed that there are two power series solutions, y1x and y2x, near the point x equal to 0. And the two solutions, the two power series solutions, are usually obtained from a recurrence relation. Okay, so the recurrence relation allows you to compute the coefficients of y1 and y2. Certain recurrence relations are good enough so that you can use them to actually get closed form formulas for the coefficients of y1x and y2x. And when this is possible, usually the closed form formulas for the coefficients will involve factorials. But in most cases, you realize this is not possible. It's not possible to have closed form solutions, closed form formulas for the coefficients. And when that is not possible, then what we do is we calculate the first few terms of the power series solutions. When I say the first few, it is actually as many as necessary. If you want 10 terms, I can do 10 terms, and if you want 10,000 terms, I can calculate 10,000 terms, as long as you have the patience and time. Okay, so that is what we have done so far. What I want to do today in this lecture is to show you how to solve initial value problems using, again, power series. And also, I'll show you that the method applies not only to homogeneous equations, it also applies to non-homogeneous equations. The method is exactly the same. So what I want to do today is I want to do an example of a non-homogeneous equation, and you will be given initial value, initial conditions. Again, we're going to focus on the case of ordinary points today, and then next time I'll look at the case of when the point is not an ordinary point. All right, so again, today we're going to look at the ordinary point case, and again, we focus on the origin. Now, the example is this. Again, it's a relatively simple-looking second-order linear equation where the coefficient function ax in this case is 1 minus x, the bx is the constant 2, and then the cx is minus x. And this time I do have a term on the right-hand side, so the equation is not homogeneous. And you have two initial conditions. Y at 0 is 1, and y prime at 0 is negative 2. Note that when you solve equations using power series method, you do not have to normalize the equation. So you work with this equation directly. Okay. So since x equal to 0 is an ordinary point, we can look for a solution in the form of y equal to summation ck xk, a power series solution. All right, so in order to solve the equation, what you do is you plug the power series together with its derivative and second order derivative into the equation. By now, you remember that every time you have a series like this, you can write y prime and y double prime in what is called the generic form. And so you plug the series y prime, and y double prime in generic form into the differential equation. Again, I suppose you already either remembered or have the formulas ready somewhere. You have generic forms for y prime, y double prime. If you don't remember, you go back to your previous lectures, you're going to find formulas for y prime, y double prime in generic form. Anyway, you plug the generic form into the equation. Now, when I plug the y double prime into the first term, then I'm going to multiply it out. I'm going to have 1 times the y double prime and then minus x times y double prime. So the 1 times y double prime is exactly the first term over here. That's exactly the formula for y double prime minus x times y double prime. So you have this y double prime, you multiply it by x, so the power becomes x to the k plus 1. So that's the second term. And then you're going to have a 2 times y prime, which is written over here. So this series is the formula for y prime. And then you have x times y. So this is the y, and you multiply it by x, so the power of x increases by 1, and that's why you get this. So you plug everything into the equation, you get 4 terms. It is the 1 times y double prime, that's 1 term, and then the x y double prime, that's the second term. 2y prime, it's the third term, and then xy is the fourth term. All right, you plug those into the equations, and then you get 4 terms like this. You get 4 power series. The next step is to, just like before, when you look at the 4 power series over here, the first and the third series, they are good. They're in generic form, but not the second one and the fourth one. They are not in generic form. So the next step is to bring those 2 series into generic form to make the x plus 1, x to the k plus 1, x to the k plus 1. You want them to become x to the k. And when you make that adjustment, you have to adjust the other k's, and you also need to adjust the starting point. And that process is called shifting index of summation. Again, it's a technique you need to master. Hopefully, you already remember this from calculus. And again, if not, you play with this shifting index of summation on paper. You write the series out term by term, and then you rewrite them in the form of x to the k. All right. So that all the 4 series will become generic form. And when I do that, I get this. So again, the first and the third terms, they remain the same, and the second and the fourth, I made some changes so that the series become generic form. Okay, they become x to the k, and then I made adjustments everywhere else. And now this new starting point will be 1 and 1 over here. So this is a very important step that you always have to perform every time you solve an equation using power series. Now the next step is to combine the 4 terms on the left into a single power series. And again, this is also a very important step you always have to do. What you need to do is you need to, when you combine the 4 series into a single one, you need to find the common starting point. And the common starting point is usually the highest starting point. In this case, it's going to be 1. You have a starting point 0, 1, 0, 1. So the common starting point will be 1. When, of course, you start from 1, you will have left out 1 term over here, the k equal to 0 term, and also 1 term over here. And you're going to write those 2 terms separately. Okay. Anyway, so you're going to combine the 4 series into a single one, and you also want to expand the right-hand side into using the binomial formula. You expand the right-hand side into 3 terms. And what I get is a long equation like this. Again, those 2 terms, the 2c2 plus 2c1, came from the k equal to 0 term over here, and also the k equal to 0 term over here. And so that's the 2c2 plus 2c1. And then starting from 1, all the 4 series are combined into a single one like this. That's one algebraic calculation that I did over here. I want to mention, you notice that the second series and third series, they look very much alike. You have a k plus 1, common k plus 1. You have a ck plus 1, ck plus 1, and you have an x to the k. So I can actually combine those 2 things. Namely, I can, when I combine those 2 things, I get this. Okay, so the second and the third are combined into this single term over here. And again, if it looks a little confusing to you, you do this on paper. You compute this slowly, and you're going to realize you have this. And then the fourth term is the minus ck minus 1. And again, the right-hand side is using the binomial formula, I expanded into 1 plus 2x plus x squared. All right, again, the main thing over here is I combine the four series into a single one, and then I expanded the right-hand side into 3 terms. The next step is to compare coefficients on the two sides. See, in the previous two lectures, the right-hand side is equal to 0. And so every coefficient on the left will have to be 0. But this time, the equation is non-homogeneous. I have 3 terms on the right-hand side. And you will see that it's exactly the same method if I have more than 2 terms. If you have 10 terms on the right side, or if you have infinitely many terms on the right side, you just compare coefficients one by one. Okay, so the constant term on the left is 2c2 plus 2c1. The constant term on the right is 1, so I get this. And then the coefficient of x on the right side is 2, that's the 2 over here. And the coefficient of x on the left, that's when the k is equal to 1, when you have x. When k is equal to 1, you calculate the numbers over there, you get this. 6c3 plus 2c2 minus c0. That's this whole thing when k is equal to 1. The coefficient of x. It has to equal to 2. And then you look at the coefficient of x squared. On the right side is 1. And on the left-hand side, it's going to be the term when k is equal to 2, if you want x squared. When k is equal to 2, see the ck minus 1 will be a c1. The middle term is 0. And when k is equal to 2, this whole thing becomes 12c4. And so that coefficient equals 1. So you have compared the coefficients for the constant term, the coefficient of x, the coefficient of x squared. And then starting from x cubed on the right-hand side is all 0. So it means this whole thing will be 0 when k is bigger than or equal to 3. And that is this. So you compare coefficients, you get something like this. And now I work with the two groups of equations over here, one group over here and another group over here. I'm going to rewrite them in a slightly different form. So I'm going to write the first group in this form. Again, you do this like on paper slowly to write the first group of equations in this form, and then the second equation, that's the main recurrence relation, I rewrite it in this form. Again, you check the details out on paper. So I get two groups of conditions like this. And then the next step, so this, once again, this is called the recurrence relation. And this time, the recurrence relation is what you call a two-term recurrence relation, because on the right-hand side, it involves two main terms, the ck plus 1 term and also the ck minus 1 term. And when you have a two-term recurrence relation, chances are you will not be able to get a formula for ck, a general formula. So what I want to do is I just want to calculate the first few coefficients. And exactly how many coefficients you want to calculate depends on the specification. Let's suppose in this case I want to calculate, say, the first 7 non-zero terms. Okay. Suppose I want to calculate the first 7 non-zero terms of the power series solution. Then what I do is this. I'm going to begin with the initial conditions. So remember, the initial conditions earlier was y0 equal to 1, and that tells me that the c0 will be 1, because c0 is equal to y at 0, and it's given the value 1, so I get c0 equal to 1. And the c1 is going to be y prime 0. And remember the y prime 0, that's the second initial condition, it was 2. So the c1 will be negative 2. And you might be wondering, how do I know those relations? In general, the relationship between the Taylor coefficients and the function is given by this. It's the case derivative at the point 0 over k factorial. That's the coefficients. So for example, if I want C2, I will look at y double prime 0 over 2. But I don't know what y double prime at 0 is, so I'm not going to use this anymore. I just use the initial conditions to get C0 and C1. And then C2, I will use this formula to get the C2. If you know the value for C1, then this will get a value for C2. And once C2 is obtained, then you plug this into the second formula to compute C3. And you also use C1 to compute C4 using this formula. So now I've got C0, C1, C2, C3, C4. And for C5 and C6, I'm going to use this main recurrence relation. So once again, the details are over here. Using the first formula for C2, I got C2 equal to 5 over 2. And then using the second formula over here, I get a value for C3. And using the formula over here, I get a formula for C4. And then for C5 and C6, I'm going to use this main recurrence relation. So for example, if I want C5, all I have to do is in the recurrence relation, I let k equal to 3. That will give me a C5. And so when you plug the k equal to 3 in the right-hand side, you're going to get several terms. So I'll do the calculations in the next slide. All right. So for example, C5, from the recurrence relation, it's going to be this quotient. Now that you already know the values for C4, C2, you plug them in, you simplify, you get a value for C5. And similar for C6, from the recurrence relation, you get a formula for C6 like this. And now that you know the value for C5 and C3, you plug them in, you simplify, and you get 1 over 40. Again, you do the details on paper to convince yourself. So now what I've got is values for C0, C1, all the way to C6. And from those values, if I only want 7 non-zero terms, then I'm done. I can write down my solution like this. So the solution y, remember, is C0, C1x, C2x squared, all the way to C6x6, and more. And if you only want 7 non-zero terms, those are the 7 non-zero terms. And I plug in the particular values for C0, C1, and so on, then I get this. So this is going to be the power series solution for my initial value problem. And this time the equation is non-homogeneous, and what you get is still a power series solution. And of course, over here, I'm only writing down the first 7 terms. Again, if the equation came out of an application scenario and you want very accurate approximations, maybe you want to get like 100 terms or 1,000 terms over here. And you can do as many as you like. You can just keep using the recurrence relation. You can get as many terms as you like. Okay, so this is my example for today. Again, the main point is you can do initial value problems and you can also do non-homogeneous equations. That's the main point for today. The next lecture, we're going to consider the case when you have a point that is not ordinary. And that will be, the situation will be much more complicated. And I'm actually going to do 2 examples for the case of not an ordinary point. The next lecture will be a very special case when the point is not ordinary, and then the one after that, I'm going to look at a more general case. All right, so see you next time.